Oh my. Let's see. Oh boy, oh boy, oh boy, oh boy. Hello, everybody. Whew. How's this? I've got a big head today. Actually, I got my camera zoomed in for some crazy reason. Okay. So we're on the verge of a Thanksgiving break of some sort. Kind of a weird thing. Let's let a few more people join, and let me give you the stream over on YouTube, and I will go ahead and post it here so that people will have it here. Link copied. Okay, where are we here? Pop out. Oh, where are we? Fall. It's still fall, right? Is it still fall? All right. Getting a little cold out there. All right. Today's trivia. Let's find a good one. What is the name of the player character in Horizon Zero Dawn? Well, very good. All right. I am not even familiar with that game. I have missed that. Oh, well, this is a good one. All right. Kratos faces off against which of the 7 wonders of the ancient world brought to life at the start of God of War 2? Well, anyone? The Colossus of Rhodes. So it's a colossus. It's not exactly a god. In the original Gears of War for the Xbox 360, how many kills in ranked versus multiplayer matches were required to earn the Seriously achievement? $10,000. Okay, here's an easier one. With more than 80 million copies sold, what was the best-selling game on the Nintendo Wii? 80 million? 80 million. Wii Sports, yes, it does. Yeah. 80 million. Wow, that's such a big number. That's incredible. There are that many Wiis? That's awesome. Yeah, that's damn. All right. So, how's everybody doing? We're at whoops, we're not at critical mass, but we'll take it. We're at 2, 4, 6, 8, 10, 12. All right, that's more than half of 20, I suppose. So we'll go with that, and everyone else will catch it later, hopefully. Absolutely. Yes. Importing sprites, I assume, right? We're talking about graphics? Yes. Okay. No. Okay. Just to be sure of this, and a few people did ask and got a little nervous. Okay. Officially, the rules are no imported scripts. That's no imported scripts, no imported assets from the asset store that are beyond graphics, right? Graphics and sound, fine. The scripts that accompany them, the scenes that accompany them, nope, don't use those. So we don't want to use that. No bolt graphs, other than you can write your own bolt graphs and so on, totally fine. But no pre-built things. So it's move the camera yourself. It's no cinema machine. It is no use of UI modeler or UI builder or none of those. The Unity asset store. There's tons and tons and tons of stuff you can buy there that make your first person shooter building block kit. Nope. Don't use that in this class. This class is about fundamental principles. Okay. It's about getting your hands dirty, about just saying, okay, this is the basics. And the good news is whether you're using Unity or using anything else for that matter, these concepts are going to apply. Whereas if you use Cinemachine and then you go over to Unreal or you go over to Godot or something, it's entirely different, right? So we're trying to really talk about the fundamental concepts. You move a camera by doing this, you interpolate the motion, that sort of thing, right? So that's why assets are fine in terms of graphics and sound, because those are common things. But the idea of scripting here, and even in the visual programming part of things, and Bolt is certainly, Bolt itself is specific to Unity, but things like Unreal has blueprints and other tools. Visual scripting, visual programming is becoming something that lots of platforms have. So we want to do those as things, but we don't want to do things that limit us to a particular piece of the engine right here, more or less, and also bypass the learning process. Okay, so it's a very good question. Thank you very much for that, John. Right? Yes. Okay. All right. I'm recognizing names now, which really should scare people. Okay, so regarding Thanksgiving, regarding this upcoming week, so what my plan is, just to kind of make life a little bit simpler this coming week. And I don't know when people are getting home, and it's going to be crazy, and you're going to be home and whatever, because most of you are on or have been on campus, but now you're heading home. So, right? Show of hands? I don't know. Anyway, you're heading home. So I'm going to post some videos, or at least post links to other videos specifically about certain techniques. I'm going to show some of them today, different platformer things I've done using hinges and joints and camera motion and all that kind of stuff. Post videos, there's going to be plenty of materials, but we're not going to have a Tuesday official at our normal time lecture. That's not to say I won't be here, because I will. I'm not going anywhere. I'm still here, and I'm still going to be checking Discord, still going to be available, and so on. But I'm going to be posting other content that's not meant to be viewed necessarily during that time slot. Okay, so there'll be material and stuff and things for you to do and so on, but it's not going to be specifically at Tuesday at what time? Tuesday at this time, 2:30, right? That's where we normally are at, right? So if you are expecting something out, I'll be around. We can talk to you. You show me your game. We can stream. We can chat. You can show me your progress and so on. And that's cool, but it won't be kind of the traditional lecture sort of thing, all right? Just to make life a little bit that much easier with all this transition back and forth and all that kind of stuff. I'm going to post a bunch of things that either people email or direct message me and ask me about, or the stuff that I've done. I'm going to go over, I'll show you a bunch of different platformers and stuff that I've done for other classes in the past, and some of the cool things about those. And some of them I have specific tutorials about. We'll cover some of it today, kind of the general ideas. But I'm going to put bonus videos about specific techniques. So there's going to be more short videos, and I'll put the links. I think I have a playlist of them. I'll put the links over in Discord. There'll be a playlist where I'll share that playlist on Discord, and also make sure that that's on LMS as well, so you can kind of go through those things. So there's gonna be lots of stuff, but not an official, this time slot thing. Okay, so you can check those out. Yep, go ahead. They're going to be more in-depth demonstrations of the stuff we've already talked about, right? We've talked about hinges and joints, and we're going to talk about inheritance today, and we're going to talk about, those sort of things in general. We talked about, particle systems. We talked about things, but it's going to be more like nuts and bolts demonstrations. Some, really, if you want to use them, by all means, use them. But they're not going to be necessarily new material per se, but it's going to be more, explanation of, how you might use those in special ways, right? So if you already have some kind of clear, I'm going to use this and so on, maybe you don't need those. You should at least check them out to see, okay, is this application of hinge joints, spring joints, camera automation, is it something that I'm interested in? Check it out, so on. So there'll be good stuff available that's meant to kind of go into a deeper dive on some of the existing stuff. So by all means, you should watch it, and it will help you with regards to your platform game and demonstrating all those techniques to be better. But it's going to be more depth than new stuff. Does that make it clear? Okay. All right. So we won't worry about like new stuff per se. We're just going to, might talk a little bit about elements of design. We'll talk about that, how I used inheritance and so on, that sort of thing. So with that in mind, let's dive into inheritance, because I do want to talk about that. And it is something I'm going to expect to see you use in some way, shape, or form in your game. Similarly to how when we talk about things like interpolation and we talk about things like coroutines and so on, in the game, you see sort of the end results as you play the game, but you're going to be using them. So using them inside under the covers of the game, so to speak. And inheritance falls into that category as well. It's hard to say, look at a game and go, oh, it used inheritance there. So we're going to have a little bit more of a dialogue, either that through, your explanation when you submit your game, where you have this idea, hey, I have, so you're going to say, oh, okay, in my game, I used inheritance here, just like, that sort of thing. But it'll make sense, hopefully. All right. Let me show that on over there, and you quit seeing my big face. Okay, so let's talk about inheritance. All right. And let me do a quick poll over in the other section here. And let's see, do I have everything streaming? We're streaming, we're recording, we're over here. Yeah, everybody's getting good. Okay. Are you familiar with inheritance? You heard of inheritance? How much inheritance have you done? You've heard a little bit about it. Maybe in CS1, I think there's some discussion of inheritance. And we'll talk a little bit kind of sort of specifically about how C# uses it, but these techniques, not techniques so much as these concepts, are fairly universal when it comes to a lot of object-oriented programming languages and so on. So, sorry, just having a little bit of my watermelon water today. Some of these on a conceptual level, but also how you would use them specifically in a game. So if you've never heard of inheritance before, what is inheritance? Let's talk about that. All right. So for everybody, and how are we going to use inheritance here? Okay. So the idea, one of the big main designs of inheritance is that you shouldn't be reinventing things, and you shouldn't be copy and pasting things necessarily. Okay. So it's a way to incorporate things you've potentially already done before, or implemented before, or gone to the trouble of coming up with some wonderful implementation without copying it and reinventing it and so on. We use this inherit, right? And sometimes it's also a way to kind of organize functionality in some way so you can build a basic object and then kind of build on that object, right? So you can build on your ideas, build on concepts, build on functionality in ways that kind of leverage and help you kind of organize and structure stuff in your code. But it's this notion of, a lot of it has to do with reusability. A lot of it has to do with kind of, structure to functionality and so on, right? So one of the things you can ask yourself, is, oh, am I reinventing something in like one specific case? I just wanted to add this one thing, and therefore I have to reinvent all this other stuff. Right, that's a good case of maybe you should be using inheritance for that, because I just want to add some new feature, but I need all this other stuff that otherwise I might reinvent. So you'll hopefully start to notice things where it sort of makes sense. Now, okay, so let's talk about it from a concept point of view. The idea of inheritance is that you start with some generalization and then you end with some specificity. Okay, you have some origin point that defines the main thing about some class of things. There, I use the word class. So some main group, some main concept, right? You start with a big generalization, and then you eventually add specificity and a specificness of purpose here. So imagine you have something very general and vague called like the automobile, right? Or it could be the horseless wagon, something really, really general, right? But there's lots of things that fall into that category, right? So we have an automobile, but then technically a car, a bus, a truck, even maybe a motorcycle. I'm not sure. Let's see, automobile. I normally wouldn't think of automobile as a motorcycle, but perhaps it uses a gas-powered engine. It has wheels. It has some means of steering. So maybe we can generalize that as a go-kart, certainly, a dune buggy, all these sorts of things that generally are automobiles. They are capable of moving because of, maybe it's not even, maybe they just have, wheels and an engine and some means of steering. We're not even talking about gasoline powered, right? There's some generalization, but then we start to get specific things that are automobiles, but have certain things about them, like a car, right? A car versus a bus versus a truck versus a motorcycle. Those are more specific cases of our very vaguely defined automobile, right? In the case of a car, then there might even be more specific things. It might be, now here, we could say, well, a Ford is a certain type of car, or a BMW is a certain type of car. Certain types of buses, there's Toyota buses, Mitsubishi buses. We'll think of it this way, a little bit more. Maybe this is clearer, I think. I don't know why I haven't changed this slide. A car might be a coupe, a sports car, a sedan, a limousine, right? These are more specific cases of a car, where a car is something that's meant for certain number of passengers. It has a certain profile. It has 4 wheels, right? All the cars that fall into this category have 4 wheels. They generally have at least 2 doors. They have a steering wheel. They have an engine. Maybe it's in the front, maybe it's in the back. Okay, they have an engine, certain types, but certain things make them cars. Whereas certain things, automobiles, they're buses. And that's going to be, well, based on capacity, much larger capacity and so on. But we might have things like, your typical, your school bus versus your prison transport. Basically, they're buses, but they're going to have, more specific things to them, right? Or, your Doom Apocalypse bus that one of your friends happens to be building. True story, friend of mine. But, there's certain things that then they fall into those categories, and so on and so on and so on, until you get down to the case of, okay, I'm talking about a specific car, my car that's in my garage, right? That's a very specific car that has inherited certain things, from all sedans and from all Hondas and from all cars and from all automobiles. They've kind of gone through that whole chain, right? So it's sort of this notion of inheriting certain characteristics, just similar to like, in a family tree, things inherit certain characteristics as they go down the family tree. But here it's a little bit more abstract, right? Any questions? Right? So we start with things that we want to generalize, and we end up, as we get more and more specific, as we derive from these bases, we wind up with something more and more specific. Okay. So here's the general coding, the computer science overview of it here. Now, okay, inheritance. We define one class in terms of another, right? We have some derived class that came from some base class, right? So we have a base class, an initial existing class that has certain data and behavior. So this is sort of the general case, right? This base class has some functionality that we don't want to necessarily rebuild, but we want to use it in some other case, right? This is the automobile. We say, oh, okay, it's got an engine, it has wheels. All right, we start with that. But then we derive a class, something more specific. A new class that extends the base class is more specific than the base class. It has access to the same things that the base class has, the same general things, but we can add new things or modify those existing things, perhaps. So it might even in some cases be, a change, right? Sometimes we override a certain functionality. It might have had that, but we then get a little bit more specific. All right. Sorry, I got distracted by a request from another thing. Okay. So now in C#, right? Some of these things are going to be specific to C#. This is one of these cases that's specific to C#. Right? In C#, each class can only have one other base class. It can only derive from one other base class. Other languages allow you to kind of combine different base classes together to inherit or to derive new classes that have, multiple bases, multiple parents, sort of thing. More like, the typical family tree, mother, father, and kind of the kids have something in common with both of those. So in the case of C#, arguably to make things more straightforward, they decided that you can't have more than one base class for, like, so we have our components that we are creating, our classes within Unity, they are all derived from a mono behavior, right? They're all from that one base class. Now, one thing though, is you can chain base classes together infinitely. So what do I mean by that? I can inherit from something that inherited from something that inherited from something that inherited from something. So you can wind up adding features and features and features, or certain characteristics by having these sort of longer lineages, but you can't combine them, all at once. Now, I know some of you out there have already used something called interfaces, which we'll talk about, which is sort of like inheritance or involved in inheritance, but you can have multiple interfaces to an object or to a class, but you can't have multiple bases. You can't derive from multiple classes, right? So we can even do this with mono behavior classes and other built-ins. So we can do that. We can even create we've created our enemy behavior or our player behavior that inherited from a mono behavior, right? We could even create enemy 2 behavior that's more specific than enemy behavior was, that was based on mono behavior, right? So we can do that. We can derive from the built-in classes and then even derive new classes from the ones we derive from those classes. Whew. Exactly. So the derived class might be, oh, okay, this enemy shoots and it derived from the enemy that runs, so it can run like the one it derived from, but it can also shoot. You added that functionality to it, right? Now, there are other ways to do this, and I'll mention this now, because that is a good point. That's one of the key things. But one of the weird things that we tend to do in something like Unity, in a componentized system like Unity, you have a couple of options, right? And they're sort of outside the realm of the language and outside the realm of the normal, how we discuss inheritance in sort of a computer science-y kind of way. We are not limited to one component per game object. We've put lots of components on our game objects, right? So if we want to have a certain type of behavior, we just go ahead and we drag that script onto that game object. And we want to add another behavior, we add another one on top of that, and so on and so on and so on, right? So if you wanted your enemy to be able to shoot, you could drag onto that game object that's your enemy, you drag on the enemy movement script and the enemy shooting script, right? You can have those two scripts that you put on there. So it's sort of a shortcut around inheritance to sort of do the same thing, because we're kind of componentizing functionality, right? But in the other way to do it is to say, okay, well, I can specifically put it in my scripts, and perhaps it's more efficient because you're using fewer components and you're kind of, gaining, certain economy of doing things in the same class, as opposed to putting lots and lots and lots of classes necessarily on something. And even the idea of using prefabs is sort of, yet another area that you can, use this sort of object-oriented paradigm, as well, where I've created a prefab and I drag the prefab in. Oh, look, there's functionality I already have. Can you make a prefab that includes another prefab? Yes. You can do all sorts of, these tricks to kind of, go down the rabbit hole. But for today, we're going to talk specifically about inheritance as part of the language. And it's going to be up to you as the developer, as the programmer, to say, okay, in what cases does it make sense to use a inheritance in the language versus all these other mechanisms that the engine might give you that allows you to, do things that sort of feel like inheritance. So congratulations. Here's a good example of inheritance that you have all already done, right? In your code, chances are you've seen public, class, whatever, player movement, enemy AI, whatever, colon, monobehavior. You have inherited from monobehaviors. All Unity components inherit from monobehaviors, okay? And that's how it knows that, okay, this start function, this update function, those are things that are common to all monobehaviors, right? To all Unity components. They already have that set up. And even things like on collision, those other built-in events, those things like having a transform, those things like having, having a transform that lets you position it in the game. Those are the base things, the base variables, the base behaviors of that class that you then derive your new classes from. Okay, so you've already been using inheritance even without thinking much about it because it already set it up for you. So you write your own start function that's used inside of this class based on the fact that, it needs to have one of those and it understands what to do with one of those. Okay. Now, so we're going to backtrack a little bit, talk about some of the things that we've used so far and how now maybe they'll make a little bit more sense as we talk about inheritance in classes. Okay. The idea of permissions. So we've used public, we've used private, right? We've seen those sort of things. Normally, just the simple case is public, private. And then there's static, which is sort of a special case. The static can be public or can be private. But let's talk about public and private, right? Public means other things can see inside this class, right? Can see those objects, the game object, you can assign something to it, or this high score can see that and write to it and so on. And then we had private things where, okay, things outside of this class can't see them, right? So a derived class can only access functions and variables from the base class for which it has the appropriate permissions, just like things outside, right? But there's a special relationship between classes and the classes that they were derived from, okay? So just like anything in Unity, anything can access anything labeled public in the base class, right? There's nothing special about that relationship there. However, in derived classes, just like things in the outside world, you cannot access anything labeled private in the base class. However, what if you wanted to give your derived class some way of accessing something in your base class, but you don't want to expose it to everybody in the outside world, right? You only want the family secrets told to the people who are in the family tree, right? So you want to let them know where the secret, whatever is buried, but you don't want everybody else in the world. So for that, we have this thing called protected. Okay, so protected field or protected method, protected variable is marked. Protected marks a variable or function as visible to any derived class, but private for all other classes. Okay, so by default, things are private. They are not protected. So as you define and as you design your classes, if you want to design something that is going to be inherited from, if you're thinking that this is going to be the base class of something else, you want to be thinking about protected versus private versus public, right? Why? And why, in this case, why are you thinking about protected versus private versus public? Okay. So stop me at any point. This is good. Anybody can, shout out something, right? Everyone's got their, most people have the microphones muted anyway. But anyway, okay. So stop me at any point. This is one of these kind of conceptual lectures. So stop me if you have any questions. Okay. Inheritance is appealing in that it can be used to define a common structure on which to build similar but not entirely identical classes, right? It's appealing because we have, we don't have to reinvent the wheel. We could just say, okay, use the wheel, sort of thing. That's kind of, that's sort of the idea, right? We don't want to reinvent. We want to be more specific. We want to add spokes to the wheel, but we don't want to reinvent the, certain parts of the wheel. Right? So each derived class, which is the class that inherits the base, starts off with the base class's general functionality and structure. So they look an awful lot like the base class. And you can add additional methods and properties on top of the base class. Okay. So what if, however, so say this is the weird case, like maybe you don't want to do something just like the parent did. Maybe you don't want to, inherit their party affiliation or the way that they walk or something like that. You want to be able to fly. You have just your movement function, move function, and the move function originally was a walking sort of thing. But this new derived class, its move is actually flying, right? So we don't want to do the move. We want to do the flying part. Right? What if you want to change the base class's existing functionality? Well, you can certainly modify the base class. Right? There's a bunch of modifiers and a bunch of identifiers and keywords that help you to do this. Some of them are a little bit more optional than others. We're going to talk today as if they were required, the definite way for them to work. But there's already, in the case of Unity, in the case of C# and how they work together, they play a little bit loose with some of these, right? So be prepared to see some of these not used in this as strict a way inside of Unity, but these are the ideas. Okay. So if you're designing a base class that you want to use in certain ways and derive new things from in certain ways, in order to modify existing values, you must use the proper keywords in the base and derived classes. Okay, a virtual function, right? If you mark a function as being virtual, you're marking that function in the base class as able to be modified, right? So if we wanted that move function to potentially be changed, we would say virtual move and then go ahead and define that function like a normal function other than that virtual. Virtual means that we may decide to modify that one. And then when we create that new class that derives from that class, we can explicitly call our new move function, we'll say override move, saying, okay, this function is going to specifically override the original version of that in the derived class, right? The nice thing about doing it this way, about specifically using virtual and override, is that it explicitly lets the tools know about this relationship. You don't accidentally make a move function and a mover function, or a move function with a lowercase m and a move function with a capital M, or some difference in the number of parameters, and then forget, and then you wind up with like things that really aren't overriding one another, but instead they're, kind of adding functionality with a slightly different interface, right? So if you do things the strict way by saying, okay, mark all your base functions with virtual and your overriding functions as overrides, then you know that, yeah, the tools will enforce things and make sure things don't go kind of wrong. Exactly. Yes. So for people in the YouTube stream, you're just kind of virtual is the function in the base class that's going to be modified. Override is the one that overrides, that is in the deriving class that does that. Okay, so virtuals are in the base, override is in the derived. Okay. Now, sometimes you actually want to add some bit of functionality in the overriding function. Like maybe you want to say move, or the base class had a move function and you add your new move function as an overriding function, but maybe there was something about the original move function, or maybe you want to use the original move function and you just add to that, right? So you have the normal move function, and then you have some addition where it's like, okay, now you're spinning in addition to moving, right? Now for situations like that, where you want to add functionality or overlay additional functionality within that same sort of thing, you can use the base keyword to access the original virtual function's original behavior. So you can add things without necessarily eliminating what was there before it, right? So example here, commonly used when you want to do base behavior, then add on additional behavior afterwards. So you could say base.doStuff inside of your doStuff overriding function. Right, so we saw this thing in our code that said override doStuff, and then within doStuff it said base.doStuff. That means, okay, at that point in your code, now go back and call the original code that was in the base class. Right, so even though you override things, you can have access, you can execute the original versions as well by accessing the base class. Whew. Okay. An example. All right. So imagine we have an enemy. We have our generic enemy class. And your enemy class is based on mono behavior because we're in Unity after all. So we create something, we have a public string, and we have this string called type. We set it to equal to enemy, with public virtual void move. So, okay, when it's time to move this enemy, we call this function, and this function will say, oh, it will print enemy is walking, right? We're looking over here, right? So we have a base class enemy, and if you invoke the move method within that enemy, if you said enemy dot, or game object find get component of type enemy dot move, call that function, it would print enemy is walking, just accessing that one. But perhaps you have something about enemy, like for example, now all enemies have this important part that is called public string type. We want to make sure all enemies have that type, and from there maybe we do something. So now we're going to create a more specific version of enemy called the diver, the enemy diver, right? So the diver is based on the enemy, so it will have a type and we'll have a move. And now we're going to do some other things in here inside the inside the awake function of the diver. We're going to go ahead and modify the type, which we can do, right? This type now already exists for us because we are inheriting from the base enemy class. So we're free to say type equals whatever. And we can override that in here we're overriding it by literally writing to that variable. We don't have to override it with a function. We're just overriding the value here, right? So in this awake, we're overriding a value that was in the variable in the base class. But here now, in this part where it says public override void move, now we are overriding this functionality. So if you referenced a game object and said, okay, give me the diver component and said move, it's going to say diver is swimming. It's not going to say enemy is walking or diver is walking, because this is going to be the class, right? So we got this structure and then we kind of immediately overrode that. Okay, so that's kind of a simple, kind of weird case. We're not really using that much. Maybe there's just lots and lots of setup variables that you don't want to reinvent all the time. So maybe there's not an awful lot of functions or methods in there, but maybe there's just lots of data that you want to have in common for lots of data, for lots of classes, sure things. All right, so then we come along and we say, okay, now we want to have a boss function. This is similar to John's question about, can we add stuff, the shoot, right? We had the move, and now we want it to be able to shoot. So here's a good example of that. We can say, okay, boss enemy based on our enemy over here. During the awake event, we're going to set its type to boss. And then we're going to give it its own move function, which the boss is capable of walking, right? So if I said base.move, that's the functionality I wanted to keep. So it would say at this point, this line of code here would result in the emission of this. It'd say print boss is walking, right? Because it overrid the value in the type and then called this base function, which made it type boss is walking. And then it would print boss moves even faster than a normal enemy, right? So if you referred to, if you called the move function of one of these guys, yep, that's what it would do, right? Layer that stuff on top. Plus, we're going to add this shoot function, shoot method, that now the boss type of enemy has this shoot, right? So we can use that. And it would say boss fires at you. Whew. Now, this is sort of, I include this here as a tip or trick. I don't think I've ever seen anyone actually use this, but there are ways you can override lots of existing functionality in even base classes in Unity, like in C#. Strings are classes, right? As opposed to arrays of characters. A string is a proper class. You can override things like toString. So you could create your own string class based on a string class and override functionality in there. So, for example, toString is a function for all objects in C# to display them as a string. It is marked as virtual, so any object can override the function to set custom behavior for displaying itself as a string, right? So this common functionality here, we can play tricks with other objects because they all have this toString in C# potentially, right? So for example, we might have a card that then has a toString. So we say card toString, and it will make itself available as a string, right? Right. And some of the basic, we're inheriting from base classes, we're deriving new classes, we are overriding potentially some parts, we're using certain parts, we can use the parts that are in existence and so on. Whew. So that's one big concept of object-oriented programming, one of the pillars of object-oriented programming, inheritance. Now, one of the other pillars of object-oriented programming is called polymorphism, multiple forms, right? That's what polymorphism is, right? Something that has multiple forms. Basically means using the same name for differing methods quite often, okay? The same name for differing methods. Now, you might have noticed that when we did things like instantiate, we were given the option, sometimes we might call instantiate and pass it the game object prototype of what we're going to instantiate, and we can just go ahead and instantiate it just like that. Or sometimes we instantiate it and we pass it the position and the rotation, and we can, that's an independent instantiated game object. Or we can even instantiate it, pass it the prototype, pass it the location, pass it the rotation, and pass it the parent, in which case now it is a new game object that's parented to that, and so on and so on, right? There's multiple versions of that instantiate routine, okay? So instantiate has multiple ways of being called depending on how it's used. So that's an example sort of a polymorphism. Now, sometimes that polymorphism is compile time polymorphism when it's done within a class. Sometimes it's runtime polymorphism when it's done between classes, okay? So some of the things we can do with our inheritance and this sort of idea of polymorphism, you might have multiple types of classes, maybe you have multiple types of enemies, maybe you have things that have been, you have your diver that's derived from enemies and your boss that's derived from enemies. And how do you keep track of all these? Because ultimately you just have a move function that you want to call. Do you have to say, oh, boss.move or diver.move or player.move? Where does that all happen, right? So we have these mechanisms of compile time and runtime that you don't normally have to think too hard about these, but there are ways to use this polymorphism here. All right. So compile time polymorphism, using the same name for differing methods with differing arguments. That's sort of the case where I just explained, not sort of, it is the case that I just explained with inheritance, not inheritance, with instantiation, right? So here's a case that I might create multiple functions, and this is when you got to be careful because you can create multiple functions with the same name that take different parameters. So imagine I created the printIt function that just took an integer I, and I said print I. But then I also created a printIt function that took I and j, and it printed I with a space in between and then j. You can do both of those things, right? So I can have different methods with different arguments that have the same name. Right? That's compile-time polymorphism, because what it does, it can see that while it's being compiled, while it's getting ready to run, it says, okay, you passed 2 arguments, so I'm going to call this version. You passed 1 argument, so I'm going to call this version. Right? The compiler, the interpreter, whatever it is, the part of the language that is, putting your code into machine executable form, it's going to go ahead and call the right thing. And once it does that, it doesn't change anymore. Now it has said, okay, this is the version you meant. This is the version you meant, and it's done. Okay. Runtime polymorphism is different, though. This gets tricky because this is like, okay, well, what if you have, and this is a good case in game engines, like maybe you have a million different types of enemies that are all based on, this kind of base class, but I have, an enemy that's a diver, an enemy that's a swimmer, an enemy that's a flyer, an enemy that's a crawler, and all those different types of enemies that are all based on a common enemy. Okay, so I need some way during runtime when the program's really running to say, okay, I just shot my arrow and it hit that enemy, and it didn't know at compile time I was going to shoot and hit that enemy, or that enemy was going to run. So somehow it has to figure it out when the game is running. So that's why we're using this runtime polymorphism. Done within classes here. So imagine I have a public class called a mammal, right? And here's a mammal. And one of the things you can do to a mammal, in this case, for some reason, you can pet the mammal, right? It's a cat or a dog. That's where we're getting at with this, okay? Because after all, what other types of useful mammals are there other than cats and dogs? That's a rhetorical question. Don't need to answer that. So in the generic case, we don't give it a name for starters, but we're going to assign the name in this constructor here. So when we create a mammal, the name gets assigned mammal. All right. And if we said, okay, call the pet function on this mammal, it's going to say, okay, you pet the mammal, right? So you did this thing. So here's the generic version of mammal, the base version of mammal. But now let's go ahead and let's create our cats and dogs. Again, like I said, they're 2 useful versions of mammals. Okay, so the first one we said, all right, now we're going to have this part that says, okay, let's set up a dog by naming it dog and have some kind of overriding reaction here, overriding method that's going to say, okay, if we called pet on a dog mammal, it should say you pet the dog. You should, if you pet the dog, it should get happy and wag its tail, right? That should be what the behavior that would happen when you called pet. Wags its tail, sticks its tongue out because it's a dog. You have a cat, on the other hand. Cat gets set up. Cat has a reaction to being petted. What does it do? Okay, it will either claw you or encourage you to scratch it under its neck, because that's what cats want to do. They want to be, petted a certain way. They're not as, as just complacent as dogs, right? They have particular ways of being petted, and that's what they want, right? So they're going to enforce that. They're going to say, if petted on head, oh, good. If not, then scratch, something like that is that pet behavior. So now we have this person who comes along, and the person is just, is not a mammal for some reason. So person is just based on a mono behavior here. But the person has some number of pets. And by pet here, we mean the noun pet, not the pet action. So the person has some number of pets, and the pets are a list of mammals, because we decide, maybe this should have been pet instead of mammal. I'm going to have to change it one of these days. But we're going to have a list of pets that are all mammals, and we create that list. Fine. When the person awakes, it decides, okay, I adopt a cat, I adopt another cat, I adopt a dog. So I have a list of pets called pets, and on that list I have 2 cats and a dog. Okay. You'll notice that this list was based on mammal. It wasn't based on cat. It wasn't based on dog. Right? anything that is derived from a mammal can be put into that list, is a valid potential member of that list, right? So in the case of the apple picker game, apple dropper game, apple catcher game, whatever you wanted to call it, a lot of people did things where they just caught game objects of, just generic game objects. And that was all fine because they were all game objects. But you could have even, taken it another level if we wanted to create, well, here we're kind of clashing with our engine versus our language here. But the idea would be, okay, maybe if you dropped multiple items and you kept them in a list of dropped items, right, where you would be pointing at not at the game object itself, but some component on that game object, perhaps, right? So this would be one way to have somewhat dissimilar things in the same list as long as they were based on the same as they were derived from the same base class, right? So here we have our cat, dog. We have two cats, one dog, all on the same mammals list because cats and dogs are both mammals. Whew. Okay. So we come along now and we start the person's behavior. And the first thing the person does, of course, is the person wants to pet all of its pets. It wants to attend to all the pets. It doesn't care if they're cats or dogs. It just says, okay, pet the pets. It goes through the list and it can say, okay, for each pet in pets, pet the pet. Okay. Now, one thing you may notice here is that it said var. And I'm not a huge fan of var in this case, or in any cases. But anyway, there's a way, there's sort of a built-in way. I lied once upon a time saying that, oh, I didn't really lie. That sort of steered you in the right direction here in terms of strongly typing your variables. You should always be typing your variables with what they are because that's good practice, right? You don't wind up with things that wind up just being ambiguous. Sometimes it's okay. You can actually use this var to say, all right, I'm not concerned what this pet is. And this is going to be sort of a late typing of this pet variable, right? So I didn't declare it. I certainly wouldn't want to declare it to be a cat. I wouldn't want it to declare it to be a dog. Maybe I could have declared it to be a mammal here, but var is ambiguous enough to say, all right, we can leave that, right? So sometimes you will see this var used, and that's just a way to ambiguously type a variable. So in this example, we ambiguously typed pet, and we did the for each, which gives us, it's going to iterate through our list of pets, and for each pet, we're going to call pet. So we're going to pet the cat, pet the dog. Whew. On a roll, any questions? Ugh, I need a breath. I feel like I was just... No questions. All right. No? Anyone? Bueller? Nobody. Okay. Makes sense. Good. Okay. Oh. So let me rephrase that at least to make sure that the YouTube streams it. So the question is, where's the best place to put the code? In the parent, or in the the base class, or in the derived class? My gut is to tell you that put as much as makes sense in, of course, right? The thing is, you can play all sorts of games with that, in that you could potentially be putting things in the base class that are only used by one specific derived class, right? And it's just going to sit there. It's like in the case of pets, like maybe I built something in that in the end, it's like certainly might be, if I had anticipated the fact that all mammals had cold noses, I could have put nose temperature as a feature of the mammal class, right? When I'm really only concerned about, whether the dog has a cold nose or not, right? So it's, you should put the, and because some of this is going to be, as someone who is using the class, the things that are specific to that class should be obvious and accessible, and you don't want to go and look at a whole bunch of other code to try to track where that thing came down, just out of a sense of could have been put up up in there. So it's you want to put the things that are implemented, that are used there as high up in the hierarchy and as close to the base as possible. But if they're never used except for in these edge cases, well, then that code should have been down at the edge. All right, so it's a design question, but I think it'll become reasonably, if two things use it, well, if those two things are inherited from some other class, then that's where that should be. But if they are, if you think that, in the future, everything will use this, well, then by all means, put it in the base. All right. Okay. Good question. Very good question. All right. Now, to help you manage all of this, there's more. Wait, there's more. Okay. This is these concepts of downcasting and upcasting. You've heard a little bit about casting. This isn't ray casting or circle casting, that sort of casting. All right. In general, in a lot of languages, we talk about casting when we want to assign some, grab a pointer to some chunk of memory somewhere, right? Because this is what you would do. You just, you needed some memory somewhere in your computer to put something in, and you have just a magic number, which was, that address of that memory, and you'd be holding that address of that memory. You'd say, okay, well, what is that memory? You would cast that pointer to be a certain type, to say, okay, this points at memory, but of this certain type, and you would cast it through the language to say, okay, it is of this type, right? Because it really is just a generic number that points to memory somewhere. It's not really that structured. So you have some way to kind of cast it to comply with a type, right? Now, in the case of downcasting and upcasting, it's more a feature of managing these relationships between these base classes and derived classes. Sometimes you might want to refer to something according to its base functionality. In other cases, you might want to define to interact with something according to its derived functionality, right? So you may or may not ever use downcasting and upcasting, even though you're using inheritance. But if you're really exercising inheritance, chances are you may run into this, right? Do this sort of thing. So you can use casting to basically change an object or change the way you're referencing it, or the way that you're referring to it according to its base class or derived class, right? And that base goes all the way down, right? You can upcast way into its past history if you want. You don't only have to. You can go much further up the tree. So it's not just depending on how many levels deep you do your inheritance, you can kind of abuse this if you like. But so it's normally changing the way you're referring to an object according to its base or derived class or what its current cast is. Okay, so we call this upcasting. You don't have to worry so much about these names, but it's the syntax ultimately that's going to really be doing it. These are the conceptual terms, and there's going to be the actual ways we're going to deal with it here. So upcasting is setting a derived class to be treated like its base class. You're upcasting in its tree, in its hierarchy. So when you do this, you only have access to the base class functionality. So imagine I had that boss that we created, that the boss moved faster than our base player, but it also had the ability to shoot, right? If I were to say, I declare an enemy here. I said enemy equals, and I'm going to set that enemy object to hold the boss, right? In order to tell C#, for C# to be happy about this boss being the same type of variable as enemy, I would cast it to be an enemy. And this is normally how we cast things. We have these parentheses, enemy, right? So this will say, okay, I want to refer to this boss as if it were just an enemy, as if it were just an enemy and not a boss, right? So this enemy, I'm never going to try to call shoot on enemy here, because for enemy, that is inaccessible, right? I will, if I have overridden functionality in here, the enemy will be called with that version of that functionality. It just won't have access to, specifically created new methods and new variables within the class. Okay, so whatever version is overridden, that's when it's going to use, but not anything that's been sort of invented for that specific derived class. Right, now we have downcasting, which is down the other way. Right, converting a base class back into its derived class should only be done if it would still be a legal, legal object. For example, we could say boss equals enemy as boss, right? So once we had this enemy reference, we could then say, okay, we want to refer to something. We want to get back a way of referring to it as if it was the boss again. And you can also use this is and as. Is, you could say, is enemy boss, right? Or sorry, don't say it. You say it this way. If enemy is boss, right? So you say, if enemy is boss, then you could say boss equals enemy as boss, right? Nope. Upcasting is when you want to set the class, or cast something into a class that it has derived from. So you want to refer to it that way. Downcasting is referring or referring to a class as something it was derived into. Okay. So it's not so much this check, because in the case of downcasting, you would use, potentially even use the combination of is and as, right? But if you were trying to you have some base class, right? We have enemy at this point. So just imagine we just came across this enemy object, right? And because we have, we have the pets up here, and I have just pet, right? And I want to tell, is pet a dog or a cat, right? Here, I can't really tell anything. So if there was like something like, oh, Pat, can this pet scratch or something like that? I have no idea. So I would say, if pet is cat, right? That would tell me, try to figure out, is the pet a cat or a dog, right? If pet is cat, then I would be free to say, okay, declare a variable to hold, or a reference to hold a cat, and I could use that pet as if it were a cat, right? So here, there's sort of an implicit upcast here, because now, in the case of, you took these cats and dogs and you put them in this list just as generic pets, or generic mammals, excuse me. So that's sort of the upcast. And the is and as are being used to figure out, have these things been derived into some new form. Okay, so the portion of this, you can sort of even, you can kind of forget the upcasting, downcasting words if you like. But the concepts are the important part, where you can say, okay, if you have any variable that has been derived from a boss, or excuse me, any variable that has been derived from an enemy, you can declare a reference to that as if it were just a generic enemy, right? The nice thing is then, you have some routine that only knows how to deal with enemies, you can just do that. But if you're trying to do something specific to, reload the gun, right, you might be saying, okay, let me check first to see, I know this was a gun, but now let me check, is it a reloadable gun? And if so, reload the gun, right? Because all of your other code, you may have written some great big function that just deals with guns and does all kinds of, you can spin the gun, move the gun, leave the gun, do all this kind of stuff. That's just generic guns, and you don't want to write specific versions of that, right? That's why you would have, tell someone just, hey, I just write the gun code, right? And they would just cast anything that comes in as a gun. Okay. So some of you will just put that in your memory bank. Some of you will just forget about that and never return to it again. But someone else will say, okay, someday this is going to, you may find this useful. Hopefully you'll use a little bit of it in our project at least. But we're going a little bit down a rabbit hole here, in terms of like, this is reasonably advanced stuff. Professor Cutler, she was like, you're going to teach them about abstraction, and some people get it, some people, like, so the CS professors, oh my gosh, you're going to actually, I was like, oh yeah, they'll know about it. They'll be glad they had it. So, okay, we're gonna get to this. We're almost there. Let's get through bunches of stuff. Abstraction, the abstract class, right? Other things we can do with the classes here, why they're cool, right? You can mark a class, or excuse me, you can mark something as abstract within a class, right? Makes a class or function, you mark it as being incomplete, right? For example, you could say public abstract void do something. So what does that mean? Abstract function, or it's basically the moment you have a abstract function, your class becomes abstract, meaning it's sort of incomplete. It has a hole, it has a placeholder in it, right? So as the designer, you say, okay, I know I want everybody to do something, but there's no generic version of it. There's no generic move. There's no generic thing. I just know they need to move. I'm not going to try to put a generic move function in there. I want everybody else to, when they create one of these things, they have to create their own version, right? So I'm the master architect of my program, and I'm going to tell all my programmers, okay, create these different types of enemies, and here's the way you're going to use this class to build your enemies on. And I might have an abstraction of the move or do something function, right? So a function that is marked as abstract contains an empty body and must have its own behavior, must have its behavior overridden in the derived class, right? So who's ever then taking that class and implementing it, they have to provide a version of that. It's in some ways, it's similar to the virtual keyword. Remember, virtual said, yes, you can override this class, but abstract means you must override. You must provide an override of this class, right? So we can think of it sort of like, imagine in our mono behavior, we had a virtual start function, meaning, okay, I can provide my own start function, but I don't have to. So I can delete the start function and it's not there. If I had, if Unity, when it was defining the mono behavior class, instead had said, okay, start is an abstract method, I would have to provide a start function, right? So that's the difference here. Abstract means you have to have it. Virtual means you can override it, right? So an abstract class basically is a class that contains at least one abstract function. Note that an abstract class can never be created on its own. You never instantiate an abstract class, something of that class, because it's incomplete. It's basically just a building block for inheritance. It's just a way to sort of set up the blueprint, so not the Unreal blueprint, but just a structure for your code to eventually you say, okay, I know I'm going to have all enemies and they're all going to have to shoot, but I'm just going to derive all my enemies from there, but I don't want to give them a default shoot behavior. So instead you create an abstract class that just forces them to do that, right? So for example, now we have our inheritance, our normal case of inheritance where we had, our mammals and our pets, and right, this should look familiar. Okay, so we are free to override the pet function. If we didn't override the pet function, that'd be okay too. And it would say you pet the mammal, right? If we didn't have a pet function for dog, it would say you pet the mammal. If we didn't have a pet function for cat, it would say you pet the mammal when we called the pet function. If instead here we didn't want to have that case where we said, okay, you pet the mammal, because that sounds weird. We don't want to generically pet something. We would say instead public abstract void pet, meaning when you derive your actual class that's actually going to be used from this, we can't have a generic mammal anymore. Instead, we have to have something that derived from mammal that provided this pet function. Okay, these look the same. This one looked different, meaning this can no longer be used on its own other than declaring it in a list here. We could never really kind of reference that generically then, right? So because we have to be using things that were derived from that, even though they're in that list. Flying over your head, that's okay. It'll be there in your memory banks someday. Something you'll be walking down the street and someone will say, hey, could you help me with this abstract class? And you'll be like, abstract class? I remember that. Okay, hopefully. Interfaces. And I know at least one person used interfaces already, which I'm so happy about. An interface is a contract between itself and any class that implements it. Wow, that sounds fancy. All right. It is a contract that states any class that implements the interface must implement the interface's properties, methods, and or events. So it's yet another way of kind of creating this blueprint for saying, okay, you're going to have to, here's a bunch of interfaces. Here's a bunch of functions you're going to have to include to be a proper pet. Right? So we can say, let's create a pet interface that says, okay, it's got to be able to slobber. It has to be able to eat. It has to be able to be petted. It has to be able to poop in a box. You know, those are the things that the pet interface has to be able to do. Right? And then if we want to create a new pet, we have to, okay, comply with that interface. Right? Well, you have to use, in order to implement an abstract class, you also have to provide the abstracted function. So you do have to provide that. The interface is a much more, it's not even a class. It's not, and you can use multiple interfaces and derive things that have multiple interfaces. So an interface doesn't contain any properties. It doesn't even really kind of exist on its own at all, right? It's just saying, okay, it's just sort of a contract. It has no implementation, whereas an abstract class could have some functions that are going to be used, right? So an interface contains no implementation, only the signatures of the functionality that the interface provides. So it's kind of like it's sort of an abstraction on steroids, right? It's not the opposite. It's an abstraction sort of on steroids, right? And it's, okay, here's all the things you need to do, and I'm not going to give you anything. Whereas an abstract class might be, oh, okay, here's one thing that you need to provide, but here's this other stuff, right? So an interface is sort of a abstraction on steroids. An interface contains signatures of methods, properties, indexers, and events, right? So it can set up this blueprint, set up this thing, but it really doesn't have any code at all in it, right? It's really just there to say, okay, you have to comply with this interface. Think of an interface as an abstract class with the implementation entirely stripped out, right? It's that interface. It's the abstract class on steroids. Right? Interface doesn't actually do anything. But like a class or abstract class, it merely defines what a class that implements it will do. And the cool thing is that it can inherit and implement other interfaces as well, right? So you have a lot more flexibility in terms of how you cascade or multiple, kind of interfaces, right? So we get to I'm going to power through this, and we're going to show an example here. So collections of required undefined functions defined like a class, but you use the interface keyword instead. right? It's really just meant as a construct for inheritance, and kind of gets you around the multiple inheritance kind of issue if you want. The convention is to preference them with an I class, like I enumerator. Sounds a little bit like a coroutine, right? A coroutine is a I enumerator. So a coroutine actually implements some interfaces. Interfaces cannot contain any fields, only functions, right? Functions cannot have a body defined. They must be left blank. Do not give your functions any access modifier. They will all be public. Functions must be implemented by the class. So here we go. Imagine you had the iPet interface that says, okay, I'm going to agree that if I am asked to implement this interface, I must provide a way of being petted. If I'm going to be asked to implement this iMove interface, I must provide a move function, right? So I could come along and say, okay, define a chinchilla that derives or that implements both the iPet and iMove interface, and it would be happy and valid as long as I provided these two things in there. The compiler will give you a hard time, will give you an error if you try to, if you have something that you say, I'm gonna implement this interface, but you don't, right? And then during the actual, say you have the pet store, and in the pet store you want to access the things that are based or that implement these interfaces, like our chinchilla, for example. You could directly reference them through their interfaces, through their implemented interfaces. So we could say, okay, here's the pet function that will then be called, and I'm going to pass something that's an iPet to it, meaning, yes, this pet implements this interface, and I don't know anything else about it. I can't call a move function up here because I didn't say that it's a pet that is from the iMove, that implements the iMove interface. It only implemented that interface, right? Whew. All right, now composition. Now the good news is here, composition's easy, and it's not really even inheritance. It's just based on a has a relationship instead of an is a relationship. And this comes, we're kind of coming full circle, where now imagine our components in Unity, right? So now our objects and our components in Unity, instead of inheritance where we're worrying about all these kind of code, we now have this has a relationship instead of it is a relationship. A component isn't necessarily a particular thing, but a game object could have number of components in there, right? So inheritance is creating and managing this whole hierarchy where a cat is a mammal, is a pet, is a so on and so on. Whereas composition is more property based, right? Composition indicates a property. An enemy has a weapon. A game object has a rigid body. A game object has a sprite renderer, right? But in some ways, they often feel similar. And in our case, in Unity, sometimes composition is going to be more of a go-to thing than inheritance, and sometimes arguably more powerful than inheritance, because any number of classes can be used in a composition. Any number of classes can be used as components, and you can actually even do this inside the language in addition to doing that inside of the Unity engine. So for example, we've kind of done a little bit of this ourselves. We said, okay, this animal class has a public string in it. It has a public movement type in it. You can do all sorts of things. So you combine within the class, you just add components to it by declaring them as variables, as things within the class, okay, properties of the class. Whew. And that's that. That's the whirlwind tour. You have now learned everything you'll ever need to know about object-oriented programming. No, that's entirely not true. But it does give you a pretty deep dive for one lecture into it. How much of this you're going to need to really implement, don't worry. This is just thrown out there. If you go no further than the basics, then inheritance has serve this purpose for you. The notion of saying, okay, let's get back to our abstraction here and understanding that, yes, I can create objects that derive from, or create classes that derive from other classes. That's the important part, okay? If we start to get way down into the weeds on other things, I'll help you get through that, and you'll be amazing in the long. No, anyway, okay. So now that's the whirlwind tour of stuff. Now I think pretty much you should have everything you need to develop a cool platforming game. And so what I'm going to do now is I want to show a couple of the different examples that we've had over the last couple of semesters and talk about some of the techniques and things I mentioned in the previous lecture and how they're implemented. Now, the good news is a lot of these do wind up, and this is where I'm going to give you like more specific, there'll be videos, there's some historical ones up there that kind of go a little bit deeper into some of the details on here. So these are all in the style. Anybody have any questions? Any other questions about inheritance before I just completely move off of that? Probably just heads are spinning, your mouths are dry, you're got headaches, you're freaking out. Don't worry, don't freak out. Poll. Time for a poll. Was that more about inheritance than CS1 has? All right. So in CS1, are you mostly just like, okay, here's a class and here's a derived class? Is that... Okay. Yeah. Yeah. And it's, I mean, I like to actually introduce it early on just to give you a sort of a glimpse to say, okay, you know, there's some powerful things in here. You don't need to worry about them in you know, at the beginning, but as the objects, as the things you're going to be implementing get more and more sophisticated, you should be thinking about, you know, ways to you know, use these sorts of things. And as you start to encounter them in other classes as well, you know, now you can pay more attention to say, oh, okay, someday I'm going to use this. So. Okay. All right. Very good. Now, I'm going to show you this one first, because this one I specifically used a bit of inheritance in, right? So this is, what did I call this one? The Bayat platformer. If you look on the Unity asset store, you can find from Bayat Games this particular tile map set if you want to find it. And let's play this game just a little bit, see if it still works. I'm not sure you're hearing the ticking sound or not. There's a ticking sound that actually is sort of semi-localized. So as you run around, you'll hear where this ticking sound is. And you know, so you have our little jumpy guy here. And there's all sorts of things that kind of jump up and down. Those aren't particularly deadly. Not everything is really deadly at this point. It's really just I want to show some of the wonderful frustrations of trying to get up and down different objects. Or there we go, sneak in there. Get pushed by this little animated block here. And there's one of my favorite examples of using hinges. So you'll notice throughout this game, there's a bunch of these swinging balls here, these swinging maces that have chains. They are all implemented as through using hinge joints, right? Each one of these, let me pause for a moment there. So each one of these swinging chains, there is no actual code on them. I don't know why there's an animator on them. Oh no, I know why there's an animator on them. Even the swinging part. So the reason for the animator is that's how they move, right? This part here is the actual base, and that animator is what rotates, right? So the rotation is entirely through this animator using this rotation of the object here, right? So it rotates from 45 degrees down to 45 degrees that way. And it's kind of weird because it starts off at an odd angle. So it doesn't really... Okay, it's a little bit odd. I don't know. I made my bounds a little bit odd. That's not the important part. So it animates this part, and there's a chain of hinge joints on each one of these. Each one of these is a separate link of chain. Okay, and each one has a hinge joint on it. And they're each attached to a rigid body on the previous link, right? So you'll see if I click on a particular piece of chain, there's the anchor, which is the thing that rotates, which has a rigid body on it, right? And these are kinematic rigid bodies, or at least this first one is kinematic, right? Because it's going to just rotate according to this animation. And then each chain link is a dynamic rigid body, meaning it is controlled by physics, right? And we go down the chain, each one has its own rigid body on it and a capsule collider on it that matches its geometry. Physics like that is that it's fully interactable. So I could even push that chain, you can bump into things. The rotating base is going to, of course, the moment I leave it alone, it's going to eventually kind of settle down and then be subject once again to its swinging that it can do. And I also have some moving platforms. Whoops. And the platforms move and then eventually disappear. Whoop. I think I do have an amount of life in this game. I forget. So where'd the inheritance go? Let's see if I still have the inheritance left in here. Okay. So you'll see this spinning blade here and this moving eye thing over there. Okay. And, oh, there's another one up top. This is Mace that he moves back and forth. So let's find these three guys. We've got the saw and one of our Mace 128s. So let's look at the Mace 128. And the Mace 128 has a script called Base Enemy. Basic Enemy. And this is a basic enemy. So what the basic enemy does is it has a start method, and it starts a coroutine called move enemy, right? And this is how it moves. That's all there is to it, right? It interpolates its position. It potentially shifts its eyes, and so on. Okay. Now, there's also a saw enemy. Now, the saw enemy inherits from the base enemy, which is the one, of course, that we just looked at, which handled the movement from left to right. Right. And you'll notice on here, it also said if it has an animator on it. And this is one of those cases that perhaps, if I could redo it all over again, and this code's getting a little old, maybe this shouldn't be in here because this is saying, okay, well, let's check. If this guy has some animated thing, well, we're going to change the eye shift. We're going to set this floating variable. So this code here, let's say that's not my best day looking at that in there. So the important part here is this, it's doing this movement left and right, but then the saw enemy is going to have the move left and right, but it's also going to have its own update routine that is going to rotate the object, right? So that's what's really happening here. You'll notice this guy is moving in the same way that this one would, but it's rotating additionally, right? That's the one bit it's doing in addition to that. So let's see. Right? Moves very similar, rotating itself as well. Now, I think there's yet another one where the Mace Enemy, our Mace Enemy is based on the Saw Enemy. So the Mace Enemy is going to move similarly, and it is going to rotate similarly, but it is going to also, we're going to add an additional bit of functionality to it. So it calls the start routine, and we're going to add something to the start routine here, right? It calls the original start routine, which is the one that sets up the coroutine that moves it left and right. But then it also starts another coroutine to move it up and down. And it also does some other things. It moves it up and down, and I think it also changes the color a bit. Oh, and then if somebody collides with it, let's get rid of that. Make sure it collides so we can really observe what it's doing. So this was the most specific one. So this one would rotate, move up and down, or would move left and right, rotate, and do this extra bit here, this move up and down. So it's this guy up here, I believe. It's been a while since so let's walk over. And yeah. So the other one up there that's fading in and out. Look at them all in the scene here. So we have one that rotates, or one that just moves left and right, one that rotates, and one that rotates, moves left and right, rotates, and fades in and out, and is supposed to move up and down. I don't know why it's not moving up and down, but it is at least doing the fade in and out part. Is that not? Maybe I... That one. Here, click on him. Mace Enemy scripts. Oh, I guess. Oh, I think that. The movement up and down is a little bit weird because this is animated versus this is scripted. So they're kind of overriding one another that way. But the important thing, see how it's fading in and out. That's the part that's being illustrated here, is that it is modifying this color by reducing the alpha channel to kind of fade it out and then fade it back in again. Oh yeah, this isn't even, that's weird. It's not even using that in that part of the coroutine. So this move enemy up and down doesn't do up and down anymore because that's old. Okay, so pay no attention about that. This should say IEnumerator fade enemy. Be consistent. And get rid of those. Fix code. Version that moves, spins, and fades. Right. There's also in this game, let's analyze this for a moment. There's also this little coin right here that if I touch that coin, it enables a buoyancy effector. Right. So let's move our little character, and you'll see the moment it touches that coin, there's this particle effect here. Right? The particle effect is just a particle system that's pointing up. It points some little cloud-like things up there to say, okay, I can go up there now if I can manage to get past things. Oops. Oh, I guess I turned it off. Let's turn it back on again. Maybe it's timed. So if I go in there, it's going to start to float. I'll touch it again. Get past that enemy. Come on. Oh. And float, float, float. Come on, do it. There we go. We did it. Past that guy. And so on and so on. Okay, so that's a buoyancy effect in there that says, okay, we turn that field on. Come over here. Let's see. Click on there. And there's the fountain trigger, which is this coin. Then the fountain, which has a buoyancy effector that pushes anything that's in there. It makes it float up, right? With area effectors that can kind of apply a force, a buoyancy effector. It kind of gently applies a force that keeps it within that region using the collider mask. If we show the collider mask, you can see it's this area of effect in here where you'll float to the top and then kind of bounce, kind of bounce up and down at the top there at with the buoyancy there. Now, okay, one thing, and this will also be part of some tutorials. Is it 10 after 4 already? Okay, so to wrap up, I'm going to mention this. One cool thing that that all the platformers do, there's always this notion of jumping and being grounded and climbing, and when can you do certain things? Okay, so our little hero here, you'll notice he's pretty good at, he can't really jump that much when he's in the air. So I'm clicking very loudly, so you'll notice he doesn't jump anymore. He can only jump when he's touching the ground. And he can only climb when he's sort of it's stuck to the side of objects and things like that. The way that is accomplished, and his controller is a little bit more on the complex side. So let's look at our hero and our hero controller. And what the hero does in this case, at some point, we want to figure out, are we allowed to jump? Okay. So what we can do, you'll remember casting, where we cast an object or cast a circle into the scene, where we wanted to see, okay, does this overlap with something else in the scene? Like we wanted to spawn an enemy and we don't want it to be spawning on top of items. We did this physics 2D circle cast and so on. There's another physics 2D thing called overlap box, which allows us to put a box of a certain size into the scene to see what does it potentially overlap with. So what we do is we want to do something called grounding the character. So we say, you can only jump, for example, if we know that you are in contact with the ground. So what we do here is we say, okay, if that box, which we create at the current hero's position, offset just a little bit, it's just below his feet. We say, does the box that's slightly below his feet overlap the ground? If it's true, we're allowed to jump. Right? We also have the option of moving if we're touching the ground, right? So do movement is this sort of typical movement where we are, I think here I'm moving him according to physics, right? So using the joystick, the horizontal axis, and adding a force to him left or right, depending on whether or not, so yeah, I'm going to add, this is adding a force here. You see this add force according to the direction he's facing in whenever the joystick is pushing in that direction. And that'll be another little tutorial more deep on that one. So the notion of grounding a character or grounding something says, okay, only be able to jump if you're touching the ground. We could say, okay, I could even cast a box to the left or right, or overlap a box to the left or right to figure out, okay, am I allowed to climb? Is there something that you're touching left or right? casting or overlapping using those capabilities and seeing, okay, is it touching something that is potentially climbable, right? In this case, is it the ground? If I'm touching the ground, I can jump. If not, I can't jump. Okay, so that's one way of doing it, right? It's easier to do it with a cast or an overlap than it is to do with a collision in the case of that, right? Because if you're moving along and you're trying to manage collisions with the player the whole time, it's trickier because you normally only get a collision when you first touch, or you say, is collision still happening when it's still touching? So I would argue that it's easier to use casting to see, is the player touching something. There's lots of other ways to do it, but that's one way. Other things going on in this game, these spikes, for example, they're all on a grid, and that grid actually moves up and down. That's the crusher's grid, right? And there's another grid called the drop zone grid. And all of these are the things that are figuring out, okay, can these things move, right? So I've actually animated different parts, right? There's all the crushers in there. The elevator over here, this whole section moves together. It's an animated tile map, or it's an animated grid that is using tile maps. So I could define, the different sorts of things on there. So this game relies extensively on tile maps, to create these grids and so on. And the idea of this simple game was, you got to get this coin. That's the key, basically, and somehow navigate your way up here to open the chest. Simple game. Avoid the spikes, avoid the so on. That's one simple platformer using hinges, using a buoyancy effector, using some switches, using inheritance from different enemy types, and so on. It's that one. Here's another classic, my Zombie Boy game. Again, using tile maps, kind of sparsely here compared to the other one. And this is using, it actually is using inheritance as well. You'll notice there are some zombies which are green and some zombies which are red. All zombies, if I jump on their heads, I think I can kill zombies. In the case of red zombies, I don't think they're allowed to move, whereas green zombies can move. So one set of zombies is totally passive. The other set of zombies knows how to move left and right. This also has an animated tile map that exposes itself from these boxes here. You can see any box that has this green dripping liquid means there's a buzzsaw or grinding gears or something over there. Now, there's also a effect. It zooms in, tells me, okay, that was a switch of some sort. And I died. So this one has a animated camera. I guess the other one did as well. This camera is a little bit more sophisticated, and it has certain things. When I trigger certain actions, it will zoom to certain locations on the screen. Right. So this is a little bit more of a sophisticated DIY. Let me know. Okay, that's where I'm supposed to be going. And I have my yell. I can hit Q, and there's a subscription event that all the green zombies listen to. That if I yell, if they're close enough, then they all die. So that's another game. That one doesn't really use any hinges. It just uses sort of an animated, some animated layers there. Again, animated grids to move up and down and so on, and uses some inheritance. Okay. Last but not least is another bit of a game here, and this one demonstrates a couple of different things. One of my other favorite physics cliche gizmos is the hook shot. So this is created kind of similar. It's meant to be similar to sort of the Zelda Link's classic hook shot. in which you can sort of run around here, and if you're careful, let's see, you can drop and then kind of move to different surfaces and so on, and we hit the one mouse button lets go. There is a bug, there's an old version that if you try to jump to a certain tile map, it will go to the center of the tile map, which is actually here on the screen. Now, it has a little switch here that can, you know. And the other thing that this demonstrates, just to be interesting, is you'll notice up here that there's a little character moving here. And you'll notice that these things in the game are sort of changing as if they were lit, as if they were 3D objects. And this is completely optional, but something that you can decide to take advantage of. You can, there's no reason that you can't combine 2D and 3D in a Unity game. So for example, in here, what I've done, I have placed a couple of 3D objects that are 3D, but in the same plane as the game. So for the most part, the game looks very 2D and plays very 2D, and everything, you know, the characters are 2D. But I have made sure to put colliders in the areas of something like this box, for example, which is actually a cube. But carefully, that cube has a box collider 2D on it. So as far as colliding in the world, it's really just, it's a flat collider 2D, and we can visualize it. We see it as a 3D box. And the nice thing is I have a set of animated lights. So in the game, you can see the lights kind of moving around and creating this kind of cool 3D effect. So if you're going to do your Limbo or your Inside or some kind of game that you're interested in doing that sort of thing, that's the way to do that. So we can have combined 2D and 3D elements, and you can even animate them. This is an actual animated model here. And we're officially over time. So I'll wish everyone, in case I don't talk to you directly or live between now and Thanksgiving, have a great break. Stay tuned. There will be some other stuff on there. There's one last bonus thing I was going to show. So if you want to hang around, if you're not running out the door, I've got one last thing in this particular game. That's sort of a bonus feature. It's really not required to use. If you like that hook shot kind of thing, it's kind of cool. But otherwise, have a great break. If you got to run off to dinner, by all means, do that. Otherwise, is anyone going to hang around? Give me a shout if you're going to hang around for 5 minutes. Oh, yeah, that'll be around. Yeah. I'll just keep recording. So just zoom to the end. Okay. So this is, you're going to hang around or just catch the live stream? Totally fine. Yep. A design document. Yes. So what you want the game to look like. Okay. Kind of lay out the scope, lay out some goals for your character, pencil, where do you think the traps are and so on. Try to make it, sort of a playable. If you wanted to go ahead and do that as an actual tile map and do screenshots and just include that, that's totally fine as well. But you should be, thank you for asking that. I meant to announce that at the beginning, that you should be using this time, especially the Monday and Tuesday, which you're officially still here or still somewhere or still on the clock, to at least design your games. Think about all these things that we've shown and say, okay, what do you want to implement? How do you want to get there? So that that you have a roadmap that you can execute between now and the end of the semester, and that you'll be there. And barring all complications, hopefully before you officially are leaving for Thanksgiving, or before Thanksgiving, I'll get the grades out on the project here. So thank you for bringing that up. Yes, you should have a good plan for the game, and then you're going to be implementing between, the Monday, quote unquote, the Monday you get back and the end of the semester. So hopefully you have reasonable plan. Yes. Yes, you have to submit something in at least an abstract, or in a rough prototype form by the end of class in order to qualify for working on stuff after. You can't only submit after the end of class. You have to, by the end of the class, I have to have know that, okay, worst case scenario, you'll get the grade of what you had on that class. If you don't submit anything by the last day of class, you can't fix stuff after the end of class without at least having submitted something by the last day of class. Okay. All right. Thank you for bringing it up. And so the last thing I want to show you may have noticed that in this game, the cool thing about the hook shot here, and this was a relative, oh, perfect. That worked out perfectly. You'll notice he shoots out this really cool looking chain. And the chain even kind of looks to be 3D. He's also can generally sort of climb, but he's a little stunted. So that was the one new feature that I've added to this relatively old game, was this new version of his chain here. And the way the chain is created is actually something you don't normally run across in a lot of Unity games, but it's not a 3D chain at all. It is actually a very simple thing in 2D called a line renderer. Okay, so if we look at our object here, our hero. Come on, hero. Let's lose track of him. I rewrote a smaller version of this, but then it doesn't have the. Hero. Oh, player idle 1. No wonder I couldn't find him. That one of the things it has as a child object. Oh no, sorry. As a component on the player is this line renderer. Okay. So what a line renderer is exactly what it sounds like. It renders lines. Okay. So if we look at it in the scene, it's just something that renders lines from between points. You can have multiple segments. You can do all kinds of things. And what we're always doing in this is we're just drawing a line from the player to some other point. And that gets updated all the time, depending on in the update routine. It just kind of moves, it connects to 2 points. So by default, the line render is pretty ugly. Normally, it just looks like literally like a line, like an ugly kind of line. Default line, there's what it looks like. It looks like a white line. You can just set the color of it, but that's about it, right? It looks really, really terrible. Now, in Unity, in most game engines, these things called materials, and these affect how things are rendered. And usually we see a lot more of them, materials, as we get specifically into 3D objects and how we, render meshes and how we texture them and how to do this sorts of things. But we can use these materials. We're allowed with the line render to use a material to draw the line instead of just a solid color. And so I've created here this custom material. which is called a chain, and a very odd looking representation of it. But the important thing about this chain material is it actually uses this link, and I have a single or set two links, well, 1 and 2 half links. It's just a texture. It's just an image that is transparent, and it has, you know, enough of a link to be useful. And I create, you can go on here, you can always say create material. All right, that's one of the things you can do. So I've created this material, assigned this chain link to it, and used something called a shader. Now, normally a shader is just, you know, draws the texture, but here's using an unlit transparent texture or unlit transparent shader to draw that. And then it tiles the result. So if this seems advanced, yes, it's a little bit on the advanced side. But if you're interested in, you know, the use of these kind of materials and shaders, this is what these sort of get into when you want to have something where it sort of procedurally can draw things for you. And that's why it can kind of draw or color this line more like a fill pattern. It's kind of a fancy fill pattern, you can think of it that way. So it's just drawing a line with a very fancy fill pattern to draw that chain. It's not a 3D object at all. Anyway, that's the quick version, the 10-minute version of it. I'll do a deeper dive on that. I have a deep dive already, I think, on the hook shot, but not on the texture. I'll have to do that more. All right, everybody, have a great break. See you next week, and maybe it's next week in virtually next week or something like that. Otherwise, take care. De-stress. You sent me a message, which... Oh, yes. Yes, that's fine. Yeah, I'm far more concerned about the quality of the work than a specific date until it gets towards the end of the semester when I have no choice. But okay. Again, I'm a firm believer in the quality of the work over the extenuating circumstances. All right, take care. You too.